Good afternoon, everyone. I hope you can all hear me well and see my screen in full presentation mode. Can you confirm, Katie, that this
is... that looks good.
Okay, good. Thank you. So good afternoon, everyone, and welcome to the second online workshop that is jointly organized by the InPlasTwin and PUREEF-Y projects. As a coordinator of the InPlasTwin project, it is my pleasure to start today's event with a brief overview of our project. So the InPlasTwin is an EU-funded project under the Widening Participation and Spreading Excellence program. It was launched to strengthen expertise in the analysis of micro and nanoplastic through the twinning approach, addressing one of today's most pressing environmental challenges. This is microplastic pollution. The primary objective of the InPlasTwin project is to strengthen our research and innovation capacity, in particular of the Jožef Stefan Institute from Slovenia and the Agricultural University of Athens from Greece in the field of micro and nanoplastics analysis. This is being achieved through close collaboration and targeted knowledge exchange and networking with leading European institutions, which are project partners. And in the long term, our aim is to increase our understanding on the environmental and food-related impacts of micro and nanoplastics, with a particular focus on the agriculture sector. So this goal is being achieved first, of course, by encouraging long-term collaboration and active knowledge exchange between the project partners. This approach not only builds scientific and innovation capacity of across the consortium, but also helps us to develop project management skills, especially at the coordinating institutions. At the same time, we are also placing strong emphasis on the diversity, inclusion, and ethical research practices, while increasing its broader impact by raising the visibility of partners and also, of course, awareness of the micro and nanoplastics related environmental and food safety issues. The project brings together 6 partners from 6 European countries, covering a wide range of different natural science disciplines. The JSI from Slovenia, which is also a project coordinator, and AUA from Greece are mainly focused on strengthening our expertise in micro and nanoplastics analysis, with the AUA also contributing its experience with greenhouse crop cultivation and also studying how agriculture plastics affect crop quality. Then the next 3 partners, Vito from Belgium, DTU from Denmark, and IMR from Norway, are leading experts in micro and nanoplastics analysis and, of course, support capacity building activities by providing hands-on trainings, access to specialized equipments, and advanced analytical expertise. And finally, Foodscale Hub from Serbia is leading dissemination and communication efforts, of course, expanding the project's impacts and raising awareness of plastic pollutions among the agri and food sector. So as this is a twinning project, most of the activities are primarily focused on building the capacity of partners in micro and nanoplastics analysis through a series of laboratory experiments, hands-on trainings, and knowledge exchange with the use of advanced analytical techniques. First, we studied the degradation of different types of mulching films, including conventional and biodegradable mulching films, under realistic agricultural conditions in laboratory set experiments, also to identify potential release of micro and nanoplastics. Second, we are receiving trainings in sample preparation protocols to efficiently extract micro and nanoplastics from complex environmental and food samples. Thirdly, we are also gaining knowledge on different analytical techniques, including spectroscopy and mass spectrometry for the detection of micro and nanoplastics. Some of those spectroscopy-based techniques used in our project are also going to be presented and discussed today on today's webinar. And finally, advanced mass spectrometry-based methods are being applied to investigate the organic and inorganic plastic additives that are present in mulching films, as well as their leaching and migration into environmental and food samples. Here you can see the overview of our progress and the main activities carried out during the first year and a half of the project. As you can see, a major part of our work was dedicated to extensive hands-on trainings with researchers from JSI and AUA, spending time in the laboratories of partners institutions to gain, of course, practical experiences and analytical skills in different techniques. In the second phase of our project, the knowledge gained through all these capacity building activities will be applied and tested in case study focusing on strawberries. We will investigate the potential uptake and effects of micro and nanoplastics released from the degradation of mulching films, which are widely used in agriculture to enhance crop yields. However, their improper disposal and of those films can lead to the plastic residues accumulating into the soil that can potentially also impact plant health or even enter the food chain. So strawberries were in our case chosen as a model crop because of the extensive use of mulching films for their production, making them an ideal system for studying these effects, and also this is a central focus of the InPlasTwin research component. So for this purpose, the two types of experiments are being conducted now in the second half of the project. First is the hydroponically grown strawberries will be intentionally exposed to micro and nanoplastics generated from the degraded mulching films. And this experiment is going to be performed in order to investigate whether these particles can be translocated to the edible parts of the strawberry fruit. And in parallel, also a small-scale field experiment has been carried out on a commercial strawberry farms in Western Peloponnese in Greece, using different types of mulching films to investigate their impacts on strawberry cultivation. These experiments will examine not only the potential uptake of micro and nanoplastics and plastic additives into the strawberries, but also their effects on plant health and fruit quality attributes. Of course, beyond the capacity building and research activities, we also have actively shared the project and its main results through different events, such as scientific conferences, symposia, open days, online workshops and webinars, reaching not only the scientific community, but also strawberry growers and general public. In addition, we already have one scientific publication as a comprehensive review on the analysis of microplastics in soil. And we are also fostering strong collaboration with other sister projects focused on microplastics research. And today's workshop, of course, is a great example of this synergy with the PUREEF-Y project. So finally, I would like to invite you and draw your attention to the InPlasTwin Spring School that will take place in April this year, between 20 and 24th of April at the Jože Stefan Institute in Ljubljana, Slovenia. During this one-week event, participants will explore current knowledge on analytical approaches for the detection of micro and nanoplastics and plastic additives in the environment and food. And the program will include lectures and discussions led by InPlasTwin experts, but also contributions from external specialists. So more information, also including the details on the open registration, will be available soon via our project website. So in conclusion, I also invite you to follow our website and social media channels to stay updated on our activities, results, and upcoming events. And I wish you all productive and inspiring and interesting workshop. And at this point, I would also like to extend my sincere thanks to all the speakers for sharing their work, and of course, all of you for your attention and participation. Thank you very much.
Thank you, Janja. I now pass the floor to Godlin to give a presentation about the PUREEF-Y project.
Thank you very much, everyone. And while the slides are being shared, a warm welcome as well from my side as the project coordinator of the PUREEF-Y project. A big thanks as well to the InPlasTwin team with whom we have an excellent collaboration. Thank you, Yanya, Gordana, and the rest of the team. And of course, my best regards to all our speakers and participants for a very productive and excellent scientific year ahead for all of us. PUREEF-Y is a project that focuses actually on the marine environment. And you might wonder actually where is the common point. The truth is that I'm having a nice hot chocolate at the moment. And we all wonder how much of the microplastics of the cup I am actually ingesting at the moment. And every time that I go at sea, I also wonder what kind of pollution is out there. So through the PUREEF-Y project, which is also a twinning project, we are investigating a little bit what's happening in the marine environment of Cyprus. And we focus on the past, present, and future status and mitigation for our shallow water reef biodiversity and functioning under global change. Moving on, actually, PUREEF-Y is a 3-year project that we implement with the Israel Oceanographic and Limnological Research and the university, the Autonomous University of Barcelona in Spain. Once again, the overall objective is to enable us at CMMI to make progress towards scientific leadership when it comes to chemical oceanography, marine ecology, as well as experimental design, and possibly make an impact when it comes to management plans and policy influence related to the marine pollution topic. And you can see already here some pictures of our team actually conducting some experiments at sea. Moving on, you can see that the activities of the projects are well underway, both in the water, under the water, but also more often than what we would like in actually meeting rooms for conferences, seminars, training practices, in our hangars, trying to get as much knowledge as we can to develop the insights that we need to basically save, protect, and restore the oceans. Our activities are focused around 4 main aspects. First of all, we have coordination and support activities. We have developed a scientific and innovation roadmap, and we engage in a lot of training and capacity building, both on scientific skills, but also on innovation management, as well as the impact on policy making. We have our research and innovation project that I will speak further about, and you have here today different researchers of the team that will actually give you further insights into the work that they perform. And we have a lot of networking activities, including as well a summer school that will take place in 2027. So please go to Ljubljana next April, and then you'll be welcome to Cyprus in 2027 for such activities. We have our joint webinars and seminars, sometimes in partnership with projects, as well as our joint scientific conference that is coming up. And all of this is very well supported by dissemination, communication, and outreach. About our research and innovation project, I will move to the next slide. We have actually 4 pillars. The first pillar has to do with tracking physicochemical parameters related to climate change and ocean acidification. What we are trying to do is to better understand and predict the effects in the future. In Pillar 2 of our research and innovation component, we perform an ecological assessment of benthic marine biota to assess the current state of intertidal and shallow subtidal microphyte communities, biodiversity, and the health of these ecosystems. And we know that actually microplastics are one of the actually stressors to which they are directly exposed. In the third pillar, we actually sample our coastal waters and sediments. And of course, afterwards, we have to analyze all of this. And we try to obviously sample these for specific marine pollutants at key locations around our island with different rates of anthropogenic influence. The idea is also to assess pollutant accumulation over time. And we are very, of course, again here looking at different types of pollutants, including microplastics and nanoplastics. And in the fourth pillar, this is more like the testing pillar, the hands-on pillar, where we try to test the functioning of benthic communities at different ecological states in Cyprus, in order to better understand what kind of global change they are exposed to using methods that have been tested nearby in the Eastern Mediterranean. This is about our research and innovation project, and my colleagues today will speak about how they have actually applied and developed insights related to microplastics and nanoplastics in actually the marine environment. If you are interested further in our work, feel free to join on the 3rd of March 2026, the PLASTIR PUREEF-Y Info Day that will actually focus on our micro FTIR research infrastructure that is said to be provided on open access at CMMI. So maybe you would like to learn more about this, and the registration will open in the coming weeks. And we have also our scientific conference that is shown on the next slide, for which our Marine Sciences Conference of 2026 that focus, of course, on marine and coastal ecosystems, the sustainable blue economy, technological approaches and innovation in marine sciences, and 2 more topics. So if you are interested to participate, the deadline for submission has been extended till the end of the month. And to conclude, from my side, I wish you a very pleasant workshop today. Once again, great thanks. Feel free to get connected with us, not only to learn more about events and other activities, but most importantly, to build a community around our project that actually help us, of course, make progress towards our scientific goal, that also deliver value to you wherever you are in your research journey and in your career journey. We are all here to exchange and make the state-of-the-art advance, and of course engage in excellent networking opportunities. Have a great afternoon, everyone. Back to you, Kathy.
Thank you, Yanya and Godelan. And we'll now move on with the agenda for today. So the next presentation is by Dr. Olga Novillo from the Technical University of Denmark. Dr. Novillo is a postdoc who specializes in micro and nanoplastic research, combining hands-on laboratory expertise with cutting-edge analytical techniques. Olga, thank you for your time today. We look forward to your presentation.
Hi, thank you, Kathy. Can you confirm it's the slides are shown? Okay, perfect.
We can see it.
Okay. So, well, hello everyone. I'm a postdoctoral researcher in DTU, like Kathy said, and I'm here to talk about tracking microplastics with laser-based infrared imaging. For those of you who are not familiar with this, I'm checking if the slides are fast. Okay, now. So for those of you who are not familiar with this technique is relatively new. It's based in infrared spectroscopy, and so it's kind of similar to FTIR, which I know, or I guess most of you know. But it's similar, but it's not the same. So LDIR, actually, it's a laser-directed infrared imaging spectroscopy. This is the commercial name from Agilent because this is an Agilent instrument, although new options are coming out soon, probably. So yeah, it's better for that reason, it's better, I think, to call it laser cascade-based imaging. And what it does, why does it have imaging in the name, and why is it useful, really, what's the difference mainly with FTIR, is that it's combining infrared spectroscopy with image recognition analysis, basically. So what it does, it scans the sample. Is similar in that sense to FTIR. And then from this scanned image, it applies an algorithm, so it recognizes the particles on the surface, and then it will get a spectra from each particle. So it's very convenient for microplastic analysis. The source, as I told you before, the source for this spectrometry is a quantum cascade laser that it detects the polymers in the sample. And the detector, where this is very technical, right? But the detector would be mercury cadmium telluride, and this is relevant for those of you who are more in the technical or instrumental side of the projects, because if you are lucky enough to get funding to acquire an instrument, this is a difference, for example, with FTIR, that micro FTIR normally requires liquid nitrogen for refrigerating the instrument. This one has the advantage that it doesn't require that liquid nitrogen, so if it could be like a consideration to take into account. But what is it exactly LDIR, and what's important about it? As I told you before, LDIR is very similar to FTIR, really, but it has a very important difference, and we have to keep this in mind because sometimes we tend to compare LDIR and FTIR directly, and actually they measure a different part of the spectrum, let's say. So FTIR measures a wide range of wavelengths. It goes from what you will see here. It usually goes until 4,500 of wavelength, while LDIR, as it's developed to optimize, so it's optimized to analyze microplastics. They made it to focus just on what is called in the FTIR the fingerprint region, and it's the region that is used to identify the materials of what we are analyzing. And it's called fingerprint because it's the region that provides the most information for this material identification, and it's the one that is unique to each material. So if we compare, we can see the LDIR focuses on this highlighted region. This is an example from a PET sample, so polyethylene terephthalate. It's just for you to keep in mind. It's not that one or the other is better. It's just information you might need to know also, because when analyzing very complex or complex environmental samples, as well, in my field, I work mostly with environmental samples, so no pristine materials. So in my case, sometimes I miss the full FTIR spectrum because, as you know, environmental samples are often quite weathered, and sometimes having a full spectrum could provide important, or not important, but it could help discriminate between materials when we have doubts. Yeah, but moving on. So what's the microplastic analytical landscape? So as you know, well, here my colleagues are going to talk about different techniques, all of them very useful. So here I just made a table to basically highlight the differences, because sometimes if you are new to the field, it can be very confusing, but these are the more used techniques, I would say. So the LDIR, as the micro FTIR, what it measures is IR spectra, and the LDIR has a lower limit of quantification, I would say, of 20 micron. I put a star here because the lower limit could be pushed, but it's then it would be a manual workflow, because the LDIR, the main difference with other techniques is also that it's quite automated, or it can be very automated. So that's very convenient, but in automatic method, it just goes down to 20 micron. So 20 micron is not so small really these days. And well, the automatic workflow goes up to 500 micron, but this can also be pushed. The polymer is particle-based because it acquires a spectra from each detected particle. The throughput is high, and this is the main strength of the LDIR. Again, it can handle a lot of particles in a relatively fast or relatively non-labor intensive workflow, which is really nice. And yes, then you can see it's the most let's say, automated method from the ones presented here. If we have to highlight a limitation, is that in comparison to other techniques, the spectral range is limited, but it's usually enough. And yeah, the big minimum size. Micro FTIR goes down to even lower size. which would be 10 micron. Raman spectrometry goes down to 1 micron, and pyrolysis GCMS, it's a mass-based method, so it doesn't measure particles. It just provides information about the polymeric composition, but not in particles, but in mass, which is also very useful and can be complementary. And also, as always, it depends on what you have available in the lab. No technique is necessarily the best. Sorry, I'm having trouble. Okay, now it's having trouble with the slides. Okay, so this would be the LDAR. Yeah. The Raman, it's a very nice technique as well, and it goes down to smaller particles, but it requires a bit more of training, I would say, or experience. As if you work with environmental samples, you would probably face the issue of having a lot of fluorescence in your spectra. For those of you who are not familiar, although we will introduce this matter better after, is that it can mask your actual material. So it's very difficult to identify sometimes, depending on the sample. And yes, and the pyrolysis GCMS, it's also a really nice technique for for plastic identification. But as with other techniques, you have to be careful because it has the risk of giving you false positives sometimes because of matrix interference and things like that. So no single method is perfect, but going back to the LDIR, just to introduce it a bit more, it's also nice that it has like a microscope. It's not exactly a microscope, but it has like a high resolution. Well, it has optical methods coupled to the laser, so it allows you to see the particles really nicely as well. These are examples from high resolution images I've taken in the past. I'm not going to go deep into the sample prep because you had a workshop for that as well, and it would take so much time. For this, I would just say it's very similar to the rest of the techniques. There is not much change here. I mean, our aim with the sample preparation for this kind of analysis, and I'm talking again from the environmentally complex sample point of view, it's to get the samples as clean as possible. If you get the samples the cleanest, the better, because you can have a lot of artifacts and a lot of challenges when analyzing the sample later on with LDIR, but also, I guess, with any other technique, really. So our aim is always to get the samples as cleaner as possible. In our case, it depends on the sample. Every sample requires a different sample prep, but in our case, we mostly use prefiltration methods to get rid of the biggest fraction of the sample, or we divide a sample into bigger microplastics and smaller microplastics. Of course, we are always homogenize before doing this, and I usually have to digest my samples. I normally use hydrogen peroxide, and then I filter under vacuum, and then it goes into the LDIR. So pretty standard methodology. In this slide, I would just like to point out that if you guys use digestion methods, at least peroxide, in my experience, it can damage the filters that I will show you later. So in this case, I always recommend to do like a final round of filtration, adding milli-Q water or ultra pure water. So you kind of clean the filter a little bit from that chemical, otherwise it can go black and then it will hinder the LDIR identification workflow. So yes, there is another parameter that can be modified in the LDIR, and it's the sensitivity. But I will go back to this later, because more sensitivity, of course, means like more things are identified. But in my experience, sensitivity is not always, like, increasing sensitivity doesn't always give you better results, because it can actually lead to more artifacts. So I ended up, in my workflows, I usually leave it as it is. So it's like middle sensitivity. And then you have to select an area in the sample and then the LDIR uses its own algorithms to match the problem spectra with the reference spectra, like in methods like in FTIR and like in Raman even. What's specific to the LDIR is the kind of filters you have to use at the end. So what it goes into the instrument is the black support that you can see on the right normally. And these are aluminum coated filters. These filters can also be coated with gold, but of course this would be much more expensive. And aluminum coated filters are also quite expensive, but it's what it gives the best results. These really small circular filters. But there is also the possibility of using non-reflective microscope slides that are called Kevlar slides. These are much cheaper, and I usually use these ones for exploration, method exploration when I am starting a new experiment, or I have to do like a quick check for something else. I usually use these slides. These slides are equally valid, and they are also very nice to use. So it's up to you and up to what you have available in your lab. But I would say in this sense, normally if you go through a full sample preparation workflow like I showed before, then it's better to use the circular and aluminum coated ones because you get rid of some steps. Yes, that's normally if you use the Kevlar slides, you need to like filter previously with GCF filters, for example, and then you have to ultrasonicate these filters and go through a series of additional steps that increase the risk of sample loss. So the advantage of these aluminum coated filters is that you directly filter everything in that filter, so you don't lose sample. Another thing that should be checked with the LDIR is the flatness of the sample. Ideally, our samples would look like the image on the right, so pretty flat. And this little peak you can see on the right corresponds to irregularity in the surface of the filter, so particles. But if we get profiles like the ones you can see on the left, it can be problematic. And well, after you perform the LDIR analysis, you can export data like an Excel file with all the information and also with the spectra. And this is what you see in this file, so a lot of really nice info. And what we normally focus on, we need to do a lot of data cleaning and filtering because we normally only take into account matches above 0.8%, ideally 0.9, but in the environmental samples, it's very difficult to get to 0.9 in my experience. So we normally, filter out the data before because we get a lot of particles. In this Excel file, each row belongs to a particle. And then we report counts, concentrations, and size distributions. So the most important columns in this Excel file is usually the identification, which is the polymer, and the quality of the match. And then afterwards, I focus on the size of the polymers, and then I start looking for distributions and different trends. So here I'm gonna use the reference by Lopez Rosales from 2024. They have they did like a methodological study, and this together with other references and experience by analyzing samples, we got to know that we have mainly four types of sizes that we can see. So these type of sizes are like perfectly round particles or irregular fragments or perfectly shaped fibers, which usually come from textiles, and fibers that are not so perfect, so coarse fibers. And they developed this workflow to automatically classify these shapes because one of the goals by using LDIR is actually to make it as more automatic as possible. So what I did from my side is to convert this into code that can be used to automatically, semi-automatically classify particles depending on their solidity, circularity, and and the measures that are given in the in the Excel file I showed you. So here. The aspect ratio actually comes from some guidelines given by the European Union some years ago. So this combination was found to be the best to classify the particles we get in the LDIR. So you can, by using this code, you just can copy paste in your data and then you can further work in your data to see the polymer distribution. Here, I just included an example. For example, we can see in sample on the left, we got a lot of polyethylene, and in the sample on the right, we got a lot of polypropylene. The reference library provided by the instrument is quite big, but still, as in every other technique, it is recommended to enrich these libraries with your own materials. These are samples. These are different spectra from different samples. And I just like this one, for example, because you can see this polyethylene. So the blue line is the reference spectra, and the colored line, so orange and red respectively, is the problem spectra. So here the only thing that changes is the absorbance of the material itself. And these are known, like this is coming from fiber, and the right one is coming from the particle. So more not references, but more samples I got, and I like this one to show you that it's still necessary and always necessary, I would say, to double check still. So automation, it's really nice, but still it's not perfect. And actually, there are sometimes we have to double check a lot because there are some mismatches in the LDIR, and this is a continuous continuous work for us just to fine tune the matches. But you can see, so on the left, you can really see that is a really nice polypropylene match. But on the right, for example, I was getting a match also for rubber, and they are not that different really. So you have to always manually assess some peaks. These are more examples. This is from natural materials that are very often found in our samples and also in our blanks because they are everywhere. And then you can be creative, and with all this data, you can, for example, see if the shapes in your samples are linked to certain polymers. This is an example of normally not corresponding to, like, no correlation really, but for example in PET we did get that rounded particles, like PET was mostly rounded particles and not irregular, so they were quite perfect in a sense. And then, as every instrument, the LDIR faces some uncertainties, and some of these uncertainties are shared with all the techniques, I would say. So, for example, there is always some subsampling error because there's always this debate. So we sample, for example, from the sea or from soil or from a river, and if we take samples, for example, from 1 sample bottles, then 1 liter bottles, then is that representative? Then we need to do like a lot of replicates and all of this that I'm sure you've seen in other parts of the workshop. But just it doesn't have to stop you from doing your analysis. You just have to keep in mind that subsampling will always be a source of error, and you need to always report your blanks and your subsampling techniques, and always remember to homogenize your samples or your subsamples as much as possible to before filtering or before going through the full sample prep. Samples from nature are very heterogeneous, so this is also another source of error. And then in the LDIR specifically, although it's really nice for detecting, automatically detecting the particles, you need to be careful with the thresholds you put in the instrument with aggregation of fibers and particles, because as every image detection algorithm up to now, it still struggles with separating the fibers, for example, or the particles when they are clumped together. You will see an example now. So here, for example, it is, well, this filter was too complex to analyze. This sample should have been either divided in two or further diluted, because there's too many things going on for the instrument to detect them properly. And even if it detects, you can see the image on the right is the first scan of the LDIR, because before it takes a scan of the sample, and you can see all these fibers are clumped together and are recognized as one. So here we can see different colors, 1, 2, 3, 4, 5, 6 clumps, but not 6 separate microplastics, really. So we have to be careful with this. Sometimes we get underestimations in our samples because of this issue, but we need to also be careful with the overestimation, because if we put a lot of sensitivity in the instrument, the instrument will start detecting artifacts that are not really microplastics, and then we have the risk of overestimation. So it's a balance. It's finding the sweet spot. Then again, here another example of mismatching. So this was really clear to me that it wasn't a good match, because the biggest match was with rubber, but these samples, I knew where they were coming from, and I knew this fiber. I mean, it looks like a textile, and it was a textile, and it is actually cotton. And actually, then you can check with other, like the following biggest matches. So here I showed that the most consistency was with cotton, really. I mean, cellulose. So it was the first one, the bigger match was rubber, but then I saw that it was cellulose all the time. So here, the good match was really with cellulose and not with rubber. So there is always the risk of misinterpreting the matches also. But in order to reduce all these uncertainties and to try to get the most out of the instrument, the most important things I would say are make sure that you homogenize your sample unit before analyzing or before filtering. So you can also perform and report your replicates, blanks do periodically, like make blanks periodically, so you can remove these blanks then from your samples, or make the appropriate statistical approach to this, and try to always do a recovery test, because then it will give your method a lot of robustness and a lot of credibility. And for publishing is really nice for all of us then to read how it was actually done, and to avoid then misinterpretations of the data. Then always report your size, range, and detection limit. Try to ensure flatness of the sample in the case of the LDIR, because it can make a difference, and sometimes it's challenging. And always, of course, take anti-contamination measures, work in a laminar flow cabinet if possible, wear lab cotton coats, use certified materials or reference materials if possible. And again, glassware, filtration of reagents, this is common to all of the techniques, really. And double check at least a subsample of your spectra to have an idea of what's going on with your data, if it looks good, if it doesn't look good. I don't say check all of the spectra, because it's almost impossible when you have hundreds of them, but at least have a feeling of how your data is looking like. And then to conclude my presentation about the LDIR, so good thing is that the LDIR is really nice, high throughput instrument that could be fast, although in my experience, when you work with environmental samples, it's only fast if you are working with drinking water or something like that. If you are working with wastewater, with seawater, or with soil, it can take like a full day to analyze just one filter. So bear in mind, it's not that fast always. Then even if it's slow, I have to say it's convenient and easy to use because you can put the analysis in the queue and you just can leave the LDIR unattended until it finishes, and it will start the other filter by itself. So it's really nice. Then yeah, it's not a blind solution. So even if it's sold as super fast, super automated, really is not that beautiful. Like never is that straightforward when you are working with method development and environmental samples. So it needs double checking and it needs knowledge to operate it properly. The results can be strongly influenced by the particle detection settings. So this is just to keep in mind. It's not that it's good or bad. This is just you need to know what you are analyzing and how you are analyzing it. And then in automatic workflow, it's only reliable down to down to 20 micron. There is potential to go further down, but it will be in a manual way, and then therefore more time consuming, and mostly for sampling inside the filter. But still, it's a really good option. And yes, these are some of my references that, of course, you can I can share them with you if you are interested. And thank you for your attention. And if you have any questions, now it's the time, or also later on, I think there is time for a Q&A. So thank you very much.
Thank you, Olga, for all this guidance and all of these useful tips. I'm sure we will have some questions from the audience. In fact, I can see the first question is here. Ephraim asks, has anyone oxidized coralline algae with hydrogen peroxide or Fenton's reagent?
I haven't digested that sample specifically, but I've digested some similar samples. And in my case, peroxide works well. I try to avoid Fenton reaction as much as possible in my personal case, but I know it's sometimes might be necessary. I don't know if anyone in the audience has just a specific sample also that can provide input.
Okay. Another question is how you handle samples with high organic content. Are the filters damaged in that case?
So yeah, so I normally use hydrogen peroxide 30%, and I digest the samples with this peroxide at least for a couple of days, depending on the sample, depending on the matrix, sorry, for a couple of days under 50 degrees. So it can accelerate the digestion process and work more efficiently. If it's really, really, really complex, then we need to consider the Fenton reaction that the friend mentioned. And then what's important to the LDIR is that if it's still very complex, I would do a pre-filtration with an aluminum filter. And then when I filter with the LDIR filters, so the aluminum coated ones, because the peroxide can damage the filter, I do like the proper filtration, and then I add like another round at least of milky water to both get to make sure that everything from the walls has been taken out, but also because it cleans the filter and it avoids this damage of the filter mostly. Although in my experience, I've tried to analyze some damaged filters and it can work fine. Yeah, okay. But the organic matter itself is not the problem. It's the digestion method. Yeah.
Ephraim has a follow-up question. He asks if your algae were calcified, did you successfully dissolve the calcium? And if so, was hydrogen peroxide sufficient to dissolve?
I don't have, I've never had that issue, so I cannot answer to that. Maybe someone in the audience. But just to mention, related to these two questions, it's also important to, like, one of the limitations the LDIR has is that it can filter really a small volume. These filters I mentioned are only 25 milliliter in diameter. So when I have very, very complex samples, actually, I end up just being able to filter 5 ml of proper sample. And I add the triple the volume of peroxide in my case.
Okay, thank you very much, Olga. I think so that we can kind of stay on schedule, we'll now move on to the next presentation by Jenna. Just to give a brief introduction, Dr. Jenna Lee Geldenhuys is an environmental chemist. She has many years of experience in industry and currently works at CMMI as a senior associate scientist in the Marine Sciences Division. Jenna, the floor is yours.
Thanks, Kathy. I'm just going to share my screen. Let me know if you see everything fine.
Yeah, can you put it in presentation mode?
Yes.
Looks good.
Okay. So good afternoon, everybody. It's so nice to see so many participants. I'm very excited to be part of the second workshop. My name is Jenna Lee Geldenhuys, and I'm a senior associate scientist at the Cyprus Marine and Maritime Institute, and I'm currently involved in the PUREEF-Y project. The title of my talk today is Automated Microplastic Analysis with FPA-based FTIR microscopy and advanced image analysis. A quick run through of what is in store. First, a little bit about microplastics and techniques used to measure them. Then we will touch on the basics and principles of FTIR before we move on to the FTIR microscope. We will spend some time on the transformative FPA detectors, as well as the advancements in automated data evaluation. Finally, we're going to conclude with some key take-home messages. So just quickly, we all know that there's not one universally accepted definition of microplastics, but they can generally be defined as solid polymer containing particles with a polymer content greater or equal to 1% weight by weight, which are smaller than 5 millimeters and larger than 1 micrometer, arising from both direct inputs as primary microplastics, which are intentionally manufactured, or as secondary microplastics resulting from fragmentation of larger plastic debris. What's very important is that microplastics are chemically very diverse, encompassing a wide range of polymers, often with additives or copolymers that also influence environmental behavior. Now, with respect to the marine environment, microplastics are detected throughout the marine environment in all matrices, within the water column, in the sediments, in all the biota. And as depicted nicely in this image, marine systems act both as sinks and transport pathways for microplastics, allowing movement of microplastics across trophic levels, and also they act as vectors for contaminants and microbes. So all these processes ultimately link marine pollution to human exposure through the food chain and water. This highlights the need and importance for robust monitoring to support risk assessments, trend analysis, evidence-based policy, and it also highlights the need for reliable and standardized analytical methods. Speaking of, how are microplastics analyzed now? Basically, as Olga also mentioned, there are two main approaches to microplastic analysis. Mass-focused techniques based on gas chromatography with mass spectrometry that provides exact mass distributions for most common polymer types. And then we have the particle-driven techniques, which focus on the number, identity, and size distribution of microplastic particles. And this can be based on spectroscopic or microscopic methods. Now, traditional microplastic analysis often relied on manual visual sorting followed by point-based spectroscopic identification. This approach is time-consuming and prone to operator bias. Throughput is limited, and interlaboratory comparability remains a challenge. So these limitations have been clearly identified in numerous international intercomparison studies, and it really underlines the need for automation and standardization. And it's also very important to note, just as Olga mentioned, that no single analytical tool fits every challenge in microplastic characterization. Every technique has its pros and cons, so you need to choose the solution that best balances your needs, depth of insight required, and speed of analysis. And FTIR is a very well-established, fast and reliable method compared to others, which is why it was our first choice. To elaborate a little bit more as to why FTIR is optimal for microplastic analysis, it is applicable across a wide particle size range, and it is a non-destructive technique. It enables chemical imaging, and it's fast, reliable, and very well-established method that is widely accepted in the scientific community. Also, very importantly, by covering the full mid-infrared spectrum, FTIR can identify virtually all polymers, including degraded ones, including closely related copolymers, as it also extends to the nitrile band range, as well as the range of the CH and NH stretching bands, which other techniques cannot do. So since we are going to focus on infrared spectroscopy, let's have a quick look, a lightning quick look, at the fundamentals behind the technique. Now, IR spectroscopy is a chemical analysis technique that takes advantage of the interaction between infrared light and matter. As we all know, infrared light is part of the electromagnetic spectrum between visible light and microwaves. It can be further divided into three categories: near-infrared, mid-infrared, and far-infrared. Typically, when discussing infrared spectroscopy, the mid-infrared range is the type of light that is used because it coincides with important properties of chemical compounds we're interested in. So when infrared radiation is directed at a sample, it interacts with the sample and stimulates the movement of molecules and atomic bonds. This movement can take various forms. For example, using the simple water molecule, these movements include symmetric and asymmetric stretchings, as well as a lot of bending of the covalent bonds. This interaction is then detected by an FTIR spectrometer and used to create an FTIR spectrum. Now, every chemical species interacts with infrared light in a unique way, and each type of vibration will give rise to a signature peak, making each FTIR spectra like a fingerprint, unique for each chemical species. And just as fingerprints are a powerful tool for identifying people, FTIR spectra is a very powerful tool for identifying molecules and compounds. On a more practical level, there are three basic measurement techniques that we can use to do FTIR measurements: transmission, reflection, and ATR. And each one of these is useful for different types of samples. For transmission, the infrared light shines straight through the sample before being detected. This technique is useful for thin samples like tissues or films. With reflection, the infrared light bounces off the surface of the sample prior to detection, making it the technique the go-to for analyzing reflective bulk samples or samples with reflective films. The ATR uses a crystal, which is usually made of germanium. The crystal touches the sample, and the IR light passes through the crystal and enters the first couple of micrometers of the sample. Now, this technique is the most versatile of the three and can be used to analyze a wide range of samples from electronics to cloth, all without sample preparation, but it does also have its limitations. So before moving on, let's have a look at what happens inside an FTIR spectrometer. An infrared light source emits broad spectrum infrared radiation, which enters an interferometer. Here, a beam splitter divides into two beams, the radiation, that reflects off mirrors. One mirror is fixed and one is movable. The beams then recombine, creating an interference pattern that changes as the movable mirror shifts. This produces an interferogram. The light then passes through the sample and reaches the detector via an aperture. This aperture controls which part of the beam interacts with the sample and ensures that only the selected region is analyzed and not extra IR radiation. This aperture can be a simple pinhole design, or it can be flexible knife edge that precisely match the area of interest, as you can see in the image to the right. Now, in an FTIR microscope, which we will discuss next, it's the exact same concept, except a visible light source is also added, which goes to a microscope eyepiece or a camera to first of all image the sample, allowing for clear selection of the region of interest before IR analysis. Then to create the FTIR spectrum, a Fourier transform function is used to convert the interferogram into an IR spectrum showing the sample's absorbed frequencies. A reference spectrum is subtracted to remove the environmental interferences like carbon dioxide or water, and this produces a clean, high-quality spectrum very quickly. So now that we understand the fundamentals of FTIR spectroscopy, we will extend this approach by combining it with microscopy. This enables chemical identification at a micrometer scale. Now, an FTIR microscope couples spectroscopy with imaging, allowing us to identify microplastic particles and map their spatial distribution directly on filters or substrates. And as part of the PLASTER project, CMMI has acquired the Bruker 2 imaging system, which is a fully integrated FTIR microscope equipped with a focal plane array detector. And going forward, this is going to be the model that we're going to discuss and its capabilities. Some of the capabilities do include high-speed imaging, 1.6 millimeters squared per minute, over 1,000 FTIR spectra at 5 micrometer pixel size, full mid-infrared spectral range behind every single pixel. It does have a liquid nitrogen-cooled focal plane array detector. Chemical imaging is possible in transmission, reflection, and ATR, and there's also automatic switching between all detectors. Now, this instrument is going to be used to analyze all of our samples collected as part of the PUREEF-Y project, and it is considered a powerhouse when dealing with complex and heterogeneous environmental samples, which you will see now why. So let's take a quick step back and briefly look at the start of the analytical process, beginning with sample collection and preparation. Again, I'm not going to go into too much detail here, as sampling, sample handling, and sample prep were covered extensively in our previous workshop. Instead, this is just a very quick summary of the key steps typically required for complex marine samples, or actually any environmental samples, many of which have complex matrices that have their own infrared signatures. So the key message here is that no matter what spectroscopic technique is being used, sample preparation is absolutely critical. For marine samples, this generally involves a series of steps, including density separation and organic digestion to remove biological materials. The sample is also filtered in 2 stages, the first one using metal meshes to remove larger particles, and then the second one is to collect microplastics on appropriate filter material for FTIR analysis. And always, throughout the process, strict measures must be taken to avoid contamination, as Olga very nicely explained. And what's also key to this slide is that once the sample is properly mounted and prepared and mounted, the most challenging part of the workflow is essentially over. Because from there, modern micro-FTIR systems like the Lumos 2 allow the analysis itself to proceed in a completely automatic and reproducible way. So importantly, regarding filter selection for FTIR, there's a wide range of filter materials available, and the choice directly affects data quality, automation potential, and comparability. So FTIR is currently the most widely accepted approach, and depending on this filter material, measurements can either be performed in transmission, reflection, or ATR. Now for us, for routine high throughput analysis, contactless transmission measurements are generally preferred, as they offer good spectral quality and are easily automated. And for this, the anodisk filters, like the aluminum oxide filters, are currently considered the gold standard. They are IR transparent, they cover most of the relevant spectral range, and they capture particles down to sub-micron sizes. They also provide excellent visual contrast. And they're also ideally suited to both FTIR imaging and single point analysis in transmission measurement modes. And if you want to do something like a Raman spectra with FTIR spectra complementary, something like a gold filter will be the choice there. So now let's get into the key technologies that have recently advanced microplastic analysis, one of them being the focal plane array detector. So instead of measuring one point at a time, an FPA consists of 1,000 detector elements that collect spectra in parallel, allowing us to acquire over 1,000 FTIR spectra in a single scan. This enables true chemical imaging where every pixel contains a full infrared spectrum, resulting in hyperspectral datasets. Now, when we say hyperspectral datasets, we're actually saying millions of FTIR spectra. So this, instead of isolated measurements, it's a no-brainer. So compared to single point or line array approaches, FPA delivers much higher spatial resolution and dramatically faster acquisition. Also, no particles are missed. And just as importantly, FPA-based imaging underpins full automation and data acquisition, as well as polymer classification. So there are two potential pathways for microplastic analysis by micro-FTIR, and that is chemical mapping or imaging. For mapping, you would use an MCT detector and measure one point at a time or a line after detecting particles in a visual image. And it's important to note that this image needs to be a good image of high quality. As Olga mentioned, no overlap and no agglomerates, and also if the particle is transparent, it can be an issue. What's also important to note here is that there's no way to properly plan your analysis time, as it depends on a particle-by-particle approach. With imaging, on the other hand, you need an FPA detector, and you measure the entire filter at once without missing any particles. This is because evaluation is based on hyperspectral images. Remember, that's millions of FTIR spectra, and it's based on the chemical info, opposed to the mapping, which is based on the visual image itself. Also, with Lumos, you can plan your analytical time exactly because it's independent of the number of particles. It scans the entire filter with the same time every time. So this makes it really easy to plan your day ahead and to set a good routine for your lab. Imaging also has a step-by-step guidance throughout the measurements, starting with collecting the visual image, followed by automated fast imaging of the filter, and then automated data analysis with relevant software, which we will get into. It's important to note that you won't miss any particles. Even transparent or overlapping particles or agglomerated particles are detected, as it's not based on visual contrast, but rather on spatially resolved chemical resolution. The Lumos 2 does not replace good sample preparation, but I have to say it's far more forgiving of samples with complex matrices or samples that are highly contaminated, because it identifies microplastics based on chemical information. So even filters like in the image below can very, very effectively and efficiently be analyzed. So now let's take a deep dive into the second transformative advancement in microplastic analysis, and that is automation. And here we will be discussing the MPID software by Bruker. Now, classical spectral library comparisons were slow, subjective, and often unreliable. MPID overcomes these limits using machine learning, which is fast becoming the future of microplastic analysis. Its neural networks capture complex, non-linear spectral patterns, allowing for accurate classification of even degraded, mixed, or contaminated polymers, which is very, very important because nothing in nature is pristine. It processes full data sets rapidly and consistently, making it ideal for very high throughput environments. Now, some key features include superior polymer classification trained on high-quality reference data with machine learning. So the more you analyze, the more it learns, the smarter the software essentially gets. It offers reliable resolution of even crowded particles and predictable processing times, independent of particle count. The workflow is also fully automated. It starts by dividing hyperspectral images into overlapping tiles. Pixel spectra are standardized, and then a neural network extracts relevant spectral features, resulting in feature vector per pixel. All effects originating from noise and baseline variations are also filtered out at this step. Next, each pixel is classified into materials, like the various polymers, cellulose, calcium carbonate, and it also considers spatial context for smooth mapping. Lastly, connected pixels form particles, which are then scored against a reference library using a hit score, which users can tune themselves. A higher threshold for confidence matches and a lower threshold for more inclusive identification. But rule of thumb is that a default value of 800 is a good start. So from pre-processing to particle scoring, MPID turns raw hyperspectral data into reliable, regulatory-ready results. Now, the complexity and careful design of this amazing software truly deserves a talk on its own, but I have to leave it there for now. So let's take a look at a typical microplastic sample measured with the Lumos 2 image microscope. With a single click, MPID evaluates the complete data set and provides detailed and comprehensive particle statistics. The machine learning algorithm evaluates every single pixel in a chemical image, and each pixel is classified and grouped according to the polymer type, enabling robust ID even in complex environmental samples. It includes key parameters such as particle area, length, width, and polymer identity. These results can then be visualized and interactively filtered directly within the statistics window. Particle classes can be selectively included or excluded with distributions displayed as pie charts or bar charts or whatever you like. And as always, results can be exported as CSV files for further processing, reporting, or for, let's say, regulatory documents. So if we have a look at the data acquired in the software, as mentioned, substances are classed and assigned specific colors, not only for engaging visualization, but also for standardization. And this can be vibrant bar charts or pie charts or whatever floats your boat. If you prefer, you can also work on the data yourself because you are provided a comprehensive list of particles along with size, substance, identification quality, and all of this can also be generated into a comprehensive report for clients if you are doing contractual work. But Lumos 2 imaging system does not limit you to using the MPID software. You can use any other third-party microplastic classificator. Such an example is the very popular open source solution called Simple. This software was developed collaboratively between the Aalborg University in Denmark and the Alfred Wegener Institute in Germany. And this software is designed to facilitate automatic analysis of microplastics in a very standardized manner using infrared spectra data. Alternatively, if you are a tech whiz, you can also develop your own methods and simply upload your Python scripts into the software. So yes, the world is really your oyster here. Now, automation is not just about speed and convenience, it's actually a prerequisite to harmonization. If microplastic data are to be comparable across labs and monitoring programs, both measurement and evaluation must be standardized. And this is exactly the focus of initiatives such as the Eurotrom Horizon Europe project, as well as ongoing work within ISO to develop international norms for microplastic analysis. But what exactly are the expectations for a standardized workflow, and how does the Lumos 2 rate in this regard? Well, firstly, full automation. With Lumos 2, hardware control, measurement, and data evaluation are all fully automated, ensuring consistent and reproducible results every time. Second, accessibility. Standardized methods must be usable by non-experts. So Lumos 2 has a guided user interface, a step-by-step workflow, as you saw, to allow routine measurements by any trained lab user. And as I mentioned before, mounting the sample into the instrument is the most manual step involved. Third, complete particle detection and identification. Lumos 2 operates at the diffraction limit, measuring entire filters without aliquoting, and it uses the full range FTIR spectra, ensuring that no particles are missed, even in complex environmental samples. Finally, robust and reliable results. With FPA imaging, it tolerates very debris-rich samples, supports all polymer types, and combined with self-diagnostics, delivers reproducible, high-quality data that is aligned with emerging standards. So, in my opinion, I would say that it rates pretty well. So yes, we can see this instrument is amazing and it is ahead of its time, but the proof is really in the pudding. There are a broad and diverse user base of the Lumos 2 imaging system, and its reliability has really made it the tool of choice in many peer-reviewed studies using FPA imaging. I have included 3 examples here, which I thought were nice and relevant to both complex marine and agricultural matrices. Unfortunately, time doesn't allow me to discuss these nice results that I've read, but these papers have been included in the reference list, so if you are interested, please have a look. And there also are plenty more out there. And then, as briefly mentioned before and by Gotland in the intro, the Lumos 2 imaging system has been acquired as part of the PLASTER project through the Research and Innovation Foundation of Cyprus. It will be housed at CMMI as an open access infrastructure. So we invite collaboration across the entire research and innovation ecosystem. We want to enable scientists, policymakers, and industry to work together on advancing microplastic analysis and environmental solutions. We will be hosting an information day on the 3rd of March, and we will give more information about it and share contact details, so please keep this date open. And then finally, just some key take-home messages. Microplastic analysis by FTIR spectroscopy with microscopy lowers expenditure of time significantly. I think for a 25mm filter, you can do the entire filter in 3.5 hours. Fast and reliable measurements with comprehensive particle detection, impartial analysis, reduced bias and human error, which is very important for harmonization, minimum personal requirements because automation is essential, interlaboratory comparability and alignment with standards is possible. The Lumos 2 imaging system meets all expectations for standardization and is going to be available at CMMI as an open access infrastructure. So basically, in a nutshell, FTIR imaging, and specifically the Lumos 2 imaging system, is an optimal tool for analyzing microplastics in various matrices. So having said that, I would like to sincerely thank you all for your time and attention. And if you have any questions or would like to chat, feel free to contact me. And please, if you want to follow our PUREEF-Y project, follow us on social media for updates on microplastic analysis. Thank you.
Thank you, Jenna. Are there any questions from the audience? One question is about the silicone filters and how they compare to the anodisc filters. Can you use those instead?
Yes, you can. You can use them instead. They do have some limitations. So silicone filters also allow for the full mid-infrared range. The only problem is that the silicone filters it does absorb some IR light more than the anodisc filters, so it will require longer measurement times, which you have to keep in mind. It also has reduced visual contrast compared to the anodisc filters. So yeah, there are some drawbacks, but I have read and seen that they have been used very effectively and are a really good choice when using transmission mode. So yes, but it still doesn't replace the anodisc for the highest quality spectra.
Okay.